Hello everyone, this is our last lecture video, just kind of really a summation of what we've done so far with Taylor series and series in general. So all of our series information was really building up so we could use Taylor series. And now let's talk about some applications of Taylor series. Really, what we're going to use in practice is not a Taylor series, but a Taylor polynomial. All right, so remember our Taylor series looks something like this. This is our Taylor series centered at A. It goes on forever, right? Okay, and we're saying under the right conditions, this is going to be equal to my function f. Why do we bother making a Taylor series for a function f? Okay. Well, in practice, for example, on computers or in calculators, we don't have just we can't represent a function like sine of x exactly on a computer or in a calculator. So how do we calculate values of sine on a calculator? What we do is, instead of having the Taylor series, we have a Taylor polynomial. Okay, so we have this nice polynomial. Maybe it's got a lot of terms, but it's got a finite amount of terms. Okay, so we can keep those these coefficients stored in our computer, and then when we need to calculate sine of x, for example, we just plug x into this polynomial. Okay, the kind of gist of it is that polynomials are pretty easy for a computer to calculate. Okay, it's much easier for a computer to calculate something like a polynomial than sine of x. Okay, because really a polynomial is just addition and multiplication, right? Those are the only two things we need to calculate a polynomial. So that's a lot easier than something more abstract like sine of x. So we have a bunch of coefficients stored in our computer, and when we need to calculate sine of x, we plug x into our polynomial, and we get an approximation to our function. Okay, and that's the best we can do in a practical setting. Maybe that approximation is very good, and maybe that's good enough for our purposes. Maybe it's not. Okay, so we always have to be careful when we're doing this in the real world. Okay, we're not going to get an exact value a lot of times, just an approximation. So obviously computing is very important. Let's see, maybe something you've some instance where you've used Taylor polynomials and not even realized it. If any of you have taken physics 1, physics with calculus at UCF, we have an equation for a particle, right? The position of a particle. Let's say P of t is the position of a particle at time t. Position of a particle, or an object, it doesn't really matter. Okay. Let's assume that, let's see, our particle has constant velocity. Okay, what would the equation of our particle be, of position? It would be pt, let's see, we would have a starting position, right? Po, we'll call that Po. And then constant velocity. So we'll say v is velocity. So its position, the particle's position at time t would be p sub o plus v times t. Okay, not bad. What if it had acceleration? What if it had an acceleration term? Then our equation would look like this. All right. Well, this is starting to look like a Taylor series, right? Or a Taylor polynomial. And it is. And actually, let's see, we have v, okay. But our velocity v is really the derivative of position, right? So really, I could say this is p0 plus p prime of 0 times t. And then v prime would be v prime would be p double prime. Okay, maybe now it's clear that this is actually a Taylor polynomial. What if, and we can add some more terms to make it clear, what if we didn't have acceleration? What if we had jerk, which is the derivative of acceleration? If we were trying to write the equation for motion with constant jerk, that would be this. Okay, so we have this Taylor polynomial. Okay, so why are we using Taylor polynomials for these equations of motion, right? Well, if a particle has some equation, right? If, let's see, the position of a particle has this equation p, odds are that in nature it's not going to be a nice equation with nice coefficients, right? It's probably going to be some, if such a function exists, it's going to be probably really weird. Let's say p of t is very complicated. Maybe it's, if we wrote it as a polynomial, maybe it'd go on forever. Maybe it'd have an infinite amount of terms. Okay, so maybe it's got some true form that is super complicated. But how can we deal with that in our calculations on computers and calculators, things like that? Well, we could simplify it by approximating it with a Taylor polynomial. Okay, so we say maybe the equation is very complicated, but we approximate it with this Taylor polynomial, and now we can deal with it in our calculations. All right, so when you see these equations of motion in physics, if you haven't taken physics already, just keep in mind that it's a Taylor polynomial. So Taylor polynomials are just one way to approximate functions, but it's kind of a classic way. So if you studied anything like math for computing, you would see Taylor polynomials probably like in the first week. It's really a classic example of how to approximate functions. All right, so whenever we approximate a function, we would like to have some idea of what the error is, right? So let's say we have our function f. Our function f under the right conditions is going to be exactly equal to the Taylor series. Okay. But when we use the Taylor polynomial to approximate f, we're going to have some sort of error, right? So if we only have k terms, it's not going to be exactly equal, but it should be about equal. But how good is our approximation, right? If we have a huge error, if our error could be 100,000, well, that approximation's just garbage then, right? We would like our error to be very small. And the good thing about Taylor polynomials is that we get an estimate of the error. We can never know exactly what the error is, because if we knew exactly what the error was, then we would know, we could just combine the error with the approximation and get the exact value. But if we have an idea of the maximum value of the error, then we can gauge how good our approximation is. Okay, so let's say we have f of x is we're representing f of x with this Taylor polynomial. Okay, so again, this is just an approximation. Whenever we have this approximation, there's some hypothetical error out there. Okay, so for each Taylor polynomial, there's some error term, r k of x. We'll call it the remainder. So for each representation, there's an error. All right, and we don't know exactly what that error is, but we would like to put some bounds on it. So there's a nice, I believe it's called the Taylor remainder theorem. There's a really nice theorem that gives us a really simple form for the error, actually. So the Taylor remainder theorem says that if f of x equals this Taylor series, or let's see, if we're approximating f of x with a Taylor polynomial, we have a remainder term. Okay, and that remainder term is actually going to be this. I'll call it C. So our remainder term is going to be given by this. So what do we have here? We have the k plus 1 derivative. So if we take a Taylor polynomial up to degree k, our error is going to be determined by the next derivative. Okay, so we take the next derivative, the k plus 1th derivative, and then this c is going to be some value in our interval. So if we're approximating our function on some finite interval centered at a, okay, c, this value of c is just some point in here. And again, we don't know exactly what c is going to be. Okay, maybe c is over here, maybe C is over here. We don't know where C is. So there's still some I don't know, unknown quality about this because we don't know what C is. So what good is this? What good is this theorem? Well, let's say that, I'll draw this picture of the interval again. Let's say we are working on this interval. Okay, so we're approximating something on this interval. We're trying to approximate our function here. And we know that everywhere on this interval, let's say fk plus 1 of x, everywhere on the interval, let's say that's always less than 7, for example. Okay, well then I know I have some idea of what this size of this remainder is going to be. So if I take, let's say I take 10 terms of my Taylor polynomial. Okay, my derivative, my error function, my remainder function is going to be what? It's going to be the 11th derivative at some point C, 12 factorial. Okay, and well, let's pick a particular interval. Let's say we're approximating a function on the interval -1 to 1. Okay, so our center would be 0. So our remainder term looks something like this. But from what I said here, our k plus 1th derivative is less than or equal to 7. So we know that our error term should be less than or equal to, let's see, 7 over 12 factorial, x to the 12th. And let's see, since x is less than or equal to 1, we'll say the error is less than 7 over 12 factorial, 1 to the 12, which is equal to just 7 over 12 factorial. Okay. So this is a good estimate of the error. The 12 factorial gets pretty big, right? So our error is pretty small. And we can see if all the derivatives, like if the 100th derivative is still less than 7, then let's see if we take 100-degree Taylor polynomial and consider remainder of 100. Our error would be less than or equal to this, right? Well, actually, see, our remainder would be equal to this at some point C. We don't know where C is, but since the derivative is bounded, we could say it's less than or equal to this. And now this is getting really small, right? So if our derivatives are all bounded, we can make our error as small as we want just by taking more terms of our Taylor polynomial.